Okay, so sorry, Oscar. I'll let you proceed, and I'll jump to the next slide here.
All right. So I just want to mention that I'm going to focus on the very high level view of how, what are the programming models that we support to program the DPU, and then the different ways you can think about it, mostly from the HPC perspective, applications. So when we think about how we can program a DPU, we can think about it as three main models that we can use for programming. One of the modes is basically what we call the offloading programming model, where basically we have a node, a compute node that is going to offload certain operations to the DPU, and then that can be used to basically use the accelerated units in the DPU to accelerate the operations there. Or it could also be used for basically achieving a little bit of an overlap, basically, where you offload the communication, an operation to the DPU, and the DPU will compute something, and the host can continue executing something. Basically, so the DPU will free some resources from the host node or the compute node, so that you can definitely achieve not only the overlap, but also basically a gain from the resources that we have in the DPU to get performance. So the programming models that support this as of today is MPI in the context of OpenMPI that can be used to offload operations in MPI, in particularly collective operations that are beneficial to run on the DPU. Not all of the collectives are beneficial to run on the DPUs, to offload it to the DPUs. And then there is the other programming model that is OpenMP offload, which is a directive-based programming model that we can use to specify a target architecture or an accelerator. And that programming model allows you to offload not only network operations to the DPU, but also some computations as well. So we feel like that's also an interesting way that we can use to program the DPU. And in this tutorial, definitely we're going to be focusing more on OpenMPI, but we also want to highlight that OpenMP offload is also supported in basically, and we're going to be having a preview of what this looks like. And for supercomputing this year, there's going to be a formal announcement of the full support for OpenMP offload to support to the DPU. So why do we care about it? So because we see that, for example, MPI can be supported using collectives on the DPU. OpenMP can also be used to offload things like point-to-point communication together with some computations, and as we will see in one of the examples. The other programming model that is basically an offloading programming model that, as a result of OpenMP offload supported in the DPU, is Cocos. A Cocos backend that uses the OpenMP offload is another programming model that is mostly for C++ programmers. So those are the three basically APIs that we currently have for HPC applications. However, so the other mode that we can use the DPUs is basically using them in the context of a model, like say distributed programming model, where we basically see the DPU just as another peer or node or another node that exists in the system, where we can map basically ranks directly to the different nodes. and basically, so you can map ranks to the host and the DPUs, and then each other will communicate through MPI. And that will basically, so it's not a hierarchical view like an accelerator host mode. It's more like basically a horizontal view of the model that everything is everything is mapped in the context of ranks or processing elements in the content of SHMEM. I forgot to mention as well that in one of the for offloading programming models that I don't have here in the slides, also SHMEM, and we will see some examples of that. So for the distributed programming model, yes, we have MPI and SHMEM supported. And then the other way to program the DPU is like we just see the DPU itself as a single device where we can program it, these cores with OpenMP, shared memory programming, or MPI shared memory. So basically, that's something that that the models that we can support there. Let's go to the next slide. Yeah. So in the context of how MPI is going to be supported currently, in the context of this tutorial and so on, the collectives that are supported basically in MPI are all-to-all V, all-to-all, all-gather, and all-gather V. Basically, the blocking and non-blocking versions of it. Most of these collectives kind of like can be used without changing of the application, although we will need to, if we really want to benefit from offloading some of these operations to a DPU, we may need to do some transformations in the code to achieve better overlapping of communication and computations and so on, or converting an application from blocking to non-blocking collectives. But out of the box, basically, the support in MPI is basically enabled via MPI run. And you'll see in the examples in the hands-on how that's being invoked. And the way it works is that the current OpenMPI implementation that we have, we can use, we can enable the collectives implementations via a UCC, which basically it's the Unified Communication Collectives framework that we can use to pick and select an appropriate algorithm for the collective that can be mapped to the DPU. And again, no applications are changing there. So those are the questions. So one is this, for which version of OpenMPI is that supported? That will be a question for Jung. Maybe he's on mute. So the version that is supported is anything that is above 4. OpenMPI 4, it's supported. However, there is a version that is in the HPC cluster that can be used to test that out. I don't know if that's something that we can basically point out to people. I don't know what's the status yet of how much of this is has been merged to the standard implementation of OpenMPI. But definitely it will, the support is OpenMPI 4 and beyond what we have been used to do this. Yes, correct. This is a good question. We will about how can we treat basically how to map ranks in the context of the DPUs. There is going to be an example application that we're going to talk a little bit more about that. Jeff Young is going to go into that. because definitely there is going to be an affinity mapping strategy that needs to be used on deciding how to map the ranks to the DPUs and the compute nodes. Okay, so this will definitely answer the questions. Okay, and thank you, John, for clarifying. Yes, since this is based on UCC, anything that is based on UCC any implementation is going to be able to use it. So I have seen, and I think UCC supported in OpenMP4, at least started to get supported there. Yeah. So next slide. Okay, so this next slide is going to talk a little bit about OpenSHMEM. So OpenSHMEM is also being supported. Basically, it's a different implementation that we have today with OpenMPI. But it's currently available. It is using basically it's using UCC, but it uses also a runtime to do aspects of the offload to the DPU. And currently, it is definitely enabled basically to support the collectives and so on in SHMEM. And they are basically there are some benchmarks that are being shown that that we can achieve overlap between the compute and between the compute node and the DPUs as we increase the data sizes. And then there is also a significant improvement in the bandwidth when we do that in the context of the all-to-all benchmarks. We're just going to show a slide that was provided by Manju and his team in the next slide. And I just want to mention as well that maybe go back to the previous slide, is that enabling the DPU basically it's also can be enabled at command line with, in this case, OpenSHMEM run or OSH run, where we basically enable UCC in the command line, and then we specify the MCA to be basically for the collectives and use basically the UROM runtime and so on. So basically, and then the application executable. So it doesn't require switching between running from in host only with then interacting with the network card versus offloading to the DPU. It can be done at in the runtime when you are doing a OS run. All right, next. Yes, and these are some benchmarks where you can see basically the degree of the percent of overlap and also the percent of bandwidth improvements that you get when you do an all-to-all benchmark. And basically the red line is anything that runs on the host, basically without offloading to the DPU, or basically using the just as a regular NIC, basically without the offload of the collective. And then the red one is basically when you basically run and basically deploy the all-to-all collective to a DPU. What we can see here is that you can achieve 100 overlap between basically the operation between the host and the DPU, especially when you enable that. And those extra resources definitely help. And then the other one is that basically the bandwidth and so on also improves as we increase the data sizes in bytes, and also that helps a lot in that. Next slide. Yeah. Okay, so this is the other type of programming model that we can use to program the DPUs, and this is a preview of what is coming soon. I want to basically I want to mention that we can use a programming model like OpenMP target offload, where we can mark basically specific regions in the code that we want to offload or execute in the target architecture. OpenMP is a high-level programming API that is aimed for compilers to generate the necessary code to enable this. And as a high-level API, the programming model is not really, it's meant to be hardware agnostic in a way by abstracting basically a device as an accelerator. So you could potentially run everything that is being run on a GPU, potentially could be offloaded to a DPU with basically the directive, with this target directive. However, performance is going to be different, of course, but the abstraction layer in the programming model will enable us to do that. As a matter of fact, basically there's preliminary work in this area that Barcelona Supercomputing Certain is working on using OpenMP target offload the benchmark, the spec Excel benchmarks that targets the GPU, all working on the DPU. Of course, it's not for performance, but it's just for testing the portability of the programming model, but it's possible to do that. And this is really important, especially for applications that we can use basically directives and Fortran and so on. Okay, so let's go next. Yeah, and this is just an example of potentially what OpenMP offload is going to be able to do in the context of a programming model, like potentially enabling point-to-point communication that through them, basically we can offload those point-to-point communications to a device, basically using the directives. So in the way, currently, as you remember, in OpenMPI, we are offloading the collectives. But with this could be another mechanism where we can offload basically point-to-point operations to the DPU using these directives. And I just also want to mention that this target offload is not only can be used to offload this MPI sends or MPI receives or whatever point-to-point communication you're going to be running on the DPU, but also you can do operations. Basically, you can target, you can use the ARM cores or the cores in the DPU to process certain information there before you send it in the MPI and so on. Okay, so and we will address this the questions at the end, so I can catch up on them. All right, so let's go next. Yes, and then I just want to also highlight that there is a potential use basically of DPUs, and this is something that we need to think about carefully, as UCC also supports machine learning and PyTorch, and basically through those algorithms that have been supported has the potential to offload certain collective operations there to a DPU, although this has to be basically studied a little bit more, but there is basically a capability that can be leveraged through UCC to offload some of these collectives to a DPU. Let's go to the next one. And yes, and this is just an example, basically that there is definitely a support for UCC in this PyTorch backend, and basically that can be used to support and as a fact to do it. So this is something that needs to be evaluated a little bit more, but potentially is another way that we can use basically a potential use of the DPUs. The algorithms may not be available yet, at least from UCC per se, but this is something that that can be enabled basically through UCC. Next. Okay, and then this is just a little bit of an idea of high-level directions in programming models. And that basically, as I said, through these high-level programming models, we are looking at programming these SmartNICs or DPUs with COCOS, OpenMP remote offload, supporting more PGAS languages. There is also work on supporting task-based runtimes. Like, for example, there is work that is being done on intelligence algorithms on intelligent networks that was presented at ISC, one of the DPU workshops, that talks about using the SmartNICs to offload tasks between what you run in one node and then migrate them to another node and so on to achieve better load balancing between ranks and so on. So that sort of work, that's another way of thinking that potentially we can use in the DPUs. And of course, the AI, the data analysis and AI frameworks is something that we need to keep an eye. That's a potential use of them for that. All right, so that's what I have in my session. And yes, and this is an example of a potential use of basically OpenMP target offload to program basically a DPU not only within the node but something that is remote, basically that can be that we can use to target another something in a distributed environment through OpenMP target offload. And this is something to think about from the point of view of a future direction for programming models to support remote DPUs. This could be as an example because what happens is that edge devices potentially may have a DPU that can be potentially we can offload certain operations from a data center or a compute center to an edge device that has a DPU, and we can definitely use that to offload certain operations there. This is something that we're definitely studying how we can enable and look into it. All right, so I think that's my last slide.
Great, thank you, Oscar. Other questions? I see there's a few about kind of DPU mapping for host and DPU. Are there any other questions for Oscar?
I had one more. I think, Oscar, you mentioned that some collectives perform better than others, offloaded to the DPU cores. Is there anything you can say, overall, like, all to all's good, reduction, maybe not so much?
Yes, exactly. So reductions are not good performance-wise.
Do you have
for
an
example,
intuition? Yeah, sorry. Go ahead.
Yeah. So those are basically the ones that anything that may create some latencies, basically that the DPU may increase some latencies that could be problematic for a collective. So basically, or reduce could be one.
I see.
But one of the advantages of so any collectives that can benefit from some algorithmic capabilities from those cores are also very important. So complex and very high level operations like all-to-all definitely are the ones that we see more benefit. I'm not sure if Young has any other insights on other profitable collectives that we see on the DPUs.
So theoretically, as Oscar mentioned, theoretically, there are a lot of collectives that can benefit from offloading to the DPU. And then like, for example, the bandwidth-driven collectives, if you have a large message such as auto V, or gather V, or gather that's listed there, and then something like a broadcast, they can all take advantage of this offloading capability. It is just how you are going to design an appropriate algorithm to take advantage of this extra capability provided by the DPU is the most important thing.
That makes sense.
If that answers the question, or if I need to clarify this a little bit.
It does. Thank you very much for the extra context. Thank you.
Okay, great. Any other questions from other attendees? We have one more question for you, and then we'll jump into a break. So we'll probably leave that up during the break here. So the question is, are you currently working with SmartNICs? Probably at this point, we'll take a break, probably about a 10-minute break. So we'll say if you are, feel free to fill out this this poll, and we'll come back at 5:20 here. Okay, and we're back. So just briefly, we'll check our last question here. So, are you currently working with SmartNICs? I think at the moment, most people are just kind of checking them out. So that's good to know. And we're going to jump into some application optimizations here. Switch back to that. Okay, so very briefly, I'll give an introduction and I'll hand it over to Jan. So this whole section of the tutorial is talking about kind of different strategies for how you might optimize your applications, specifically HPC applications for GPUs. And as part of that, there are kind of three things that we'll be talking about today. These are all things that we've looked at with Bluefield TPUs, probably applicable to other SmartNICs based on the architecture and the software stack. But the first thing that Yang will talk about is the Unified Collective Communication Collective Offload, UCC. We'll have a very short demo where we'll kind of show what that looks like. That's pretty complex. It is sort of low level at the moment because it is built on top of UCX. Then we'll talk a little bit about blocking and non-blocking transformations using UCC offload, an application that uses that P3D-FFT++, the C++ variant of P3D-FFT. And then I'll give a little bit longer presentation on kind of the most complicated strategy to use, which is algorithmic restructuring. So basically, if you have an application, you can potentially rewrite your algorithm to map it to both the DPU and to the host. Okay, so with that, I'll hand it over to Jan, and he's going to tell us about communication offload to DPUs.
Yeah, sure. Thanks, Jeff. So in the next few slides, I'm going to talk about the DPU offload for communication libraries. In this specific example, we're going to use UCC as the example and talking about how to offload the collectives. The next slide, please, Jeff. This slide is much more like a generic slide. So basically, if we take a look at the left-hand side, traditionally, when we run the host-only application, then we have the node, and then we have multiple MPI processes running on the node. And then we underneath that, there's a collective library. Like if you're using the NVIDIA/Mellanox HPCX library, then it has the HCO or UCC underneath that you can switch between one or the other. And then OpenMPI also has its own collective library inside as well. But when we're talking about offloading the collective libraries to the DPU, then we can take a look at it on the right-hand side. This is the approach that we're currently taking. And we can extend a portion of the collective libraries from the host side to the DPU. So both the host and the DPU, they can work collaboratively on the same collective, and then progress the collective, and then to make sure to take advantage of the extra capability that the DPU provides. So in this case, the UCC is not necessarily the UCC library that we're talking about. It could be anything else. Like for example, if you're using another different type of MPI implementation, such as Mvapage, also have their own collective libraries that they can offload to DPU as well. So next slide, please. So this slide is to answer one of the questions that was asked earlier. So if we're not using Docker, then how do we keep both the host and the DPU in sync? So here we have to talk about an infrastructure library that we developed at NVIDIA, which is called Mimosa. And this is a library that we used to run as an infrastructure on both the host and the DPU. It does not rely on Docker. This is completely implemented on top of a UCX. The purpose of this is to synchronize both the host and the DPU, and then to provide a communication abstraction layer between the two. So we can, from the host, we can notify the DPU, okay, here's some work for you to do. And on the DPU side, after it's done its work, it can also tell back to the host, okay, I've done what you asked me to do, so you can progress this collective to the next step. As an offloading library, we have some of the very common building blocks here. So first we have an engine, and then within the engine, we have the execution contexts. The most important part here that we have the notification and event system that we can send a notification between the host and the DPU. And then we also have lots of other auxiliary components or modules that can help us to better manage the resources, and then to provide all the necessary key points that is required by the collective algorithm, such as the topology management, and then the endpoint caching, the communicator caching, and then the platform configuration management, et cetera, et cetera. So this is a library which is open source that we provided the link, the GitHub links here, and then we also have the documentation here as well. So what it provides is a whole bunch of the building blocks that everyone can reuse to develop their own either the collective libraries or something else that with it. The next slide, please. So this slide shows how within the UCC that we developed take advantage of this offloading library, and then how we use it to do the communication. So the left-hand side has the host, and then running on the host, it is the open MPI process. This is MPI process, and then within that, there is the collective framework such as UCC. Then within UCC, I'm going to talk about some of the UCC concepts in the next few slides as well. But here we have some of the basic concepts like the teams that manages the communicator, and then the task which manages the actual collective here. So, and then we introduce the most offload engines within UCC. And then we use this offload engine to manage the topology and then the event system. So here you can see there's a back and forth notifications that we send directly from this offload engine to the DPU. On the DPU side, there is something we call the daemon, the offload daemon, which is sometimes we also refer that as a service process. So the service process, it has its own style offload engine, and then within there, it also has the event notification system. So by doing the communication between these two event notification systems, then as I mentioned in last slide, then the DPU can do whatever the host or the CPU tells it to do. So this is the basic architecture of Mimosa. So next slide, please. Okay, so this is the general architecture of the whole UCC. UCC here, we're referring to that as the Unified Collective Communication Library, which is a communication library developed by the community. So we're reusing this UCC, and then we did some modification. One thing that you notice here are the two of the blue boxes here. The first one is the blue box at the bottom, which is the underlying hardware or the resource abstraction. And then within the UCC framework, which is within this purple frame. So you can see that we have multiple of the transport layers, such as UCP, NICO, shift memory. And then one way to implement the communication or collective offloading is to implement the DPU as a proprietary transport layer. which is something that Oscar mentioned briefly in previous slides. But here in our example, we take a different approach. We implement the DPU offloading within the UCP transport layer. So this is how we only implement the whole thing, including both the collective and Mimosa infrastructure on top of UCX. So we don't have to introduce another kinds of complexity within UCC framework. So next slide, please. So briefly talking about some of the UCC key concepts, it has some of the abstractions such as library, context, endpoints, execution engines. And then one of the most important global abstraction is teams. So this is basically the communication groups, or within the MPI, within the MPI world, we typically call it the communicators. And then with these abstractions, we have some operations that we need to define, such as the collective operations, right? And we also have some of the other resources as the abstractions that we defined previously. Then we can define these operations and then how to create these abstractions. Like, for example, how do we create a context, and then how do we modify or destroy the context? How do we create an endpoint, et cetera, et cetera. This is the operation layer. And then for the collectives, we can, like, for example, we can build a collective, we can launch or start a collective, and then we can also finalize the collective after the collective is properly completed. For each of these abstractions and operations, we can also define a property or property set for those abstractions or operations. And then we can modify the properties on fly or create different properties for different objects for all of this. So next slide, please. So this is the UCC workflow. So when we are launching the MPI job, as I said, first the open MPI needs to initialize itself. When it initializes itself, it will also initialize all the providers, like, for example, the collective providers here. And UCC is one of such of the collective providers. So at this step, it will go through its own library initialization. And then after that, it will create the communication context. And then during the MPI, program progressing, so sometimes we probably need to create a communicator. Even if we're not creating a communicator explicitly, there is the MPI COM word being created on behalf of the user as well by the MPI library. So within UCC, to reflect that, UCC also need to create its team. And then once you're approaching to start a particular collective, such as the MPI auto or MPI auto V, etc., the UCC will also need to initialize a proper collective for this particular MPI operation as well. And then here you can see that there are multiple operations to be associated with the collective. There is init, post, test, finalize, start, complete, etc. There are multiple of the operations here. So once the MPI job is completed successfully, then the UCC library will go through its own library finalization and clean up all the resources that it creates and manages. So next slide, please. Talk about the offload stack. So this is the full picture of the offload stack that we currently use within the products that we are developing right now. So on the host side, the low-level communication library that we rely on is UCX. And then on top of the UCX is the offloading library, which is Mimosa. And then if you are not doing any of the DPU offloading, then you can skip this one and then go directly on top of that, which is the UCC. And then on top of that is OpenMPI. And then further on top of that is your user application. So on the DPU side, then the stack is a lot more simpler. So basically we have UCX because that's our low-level communication library, and then we have Mimosa, and that's it. So one thing to notice here is that both the UCX and UCC that we use in this project is modified version of the UCX and UCC, which is not currently being distributed in the master version of the UCX and UCC. But next slide, please. So here we provide links to all the versions that we use in our current demo and product development. So they are open source. So links are here. If you wish, you can go ahead to take a look at it. And then I'm not going to go into the details of them here. So next slide, please. So here I'm going to give a very quick example of how to develop using all these building blocks that I just mentioned, including both Mimosa and UCC, to develop a collective on the for DPU offloading. A typical algorithm that we use in collective is a RIN algorithm, right? So here it's a very simple cartoon that actually shows how the RIN algorithm works. Basically, for a particular MPI communicator, then we can assemble all the MPI ranks on a RIN. And then for a particular MPI rank, like for example, the one that in the middle there, so at any given time, so it can send its own data to multiple of other ranks on the RIN. Like for example, in this case, it's sending data to 3 of its neighbors on the right-hand side, which is I. If this rank is rank I, then it sends to I plus 1, I plus 2, I plus 3. And at the same time, it also receives data from I minus 1, I minus 2, I minus 3. And then when we're rotating the RIN, then the collective will progress by itself. This is a very simple example of a RIN algorithm. So next slide, please. So when we're doing the offload and when we're designing the offload algorithm, we will continue to use the RIN algorithm, but we have to do something differently. Because now we want to offload the RIN algorithm from the host side, which was originally being executed on, to the DPU. Okay, the way to do it is using just the 2 ranks as an example. Here we have the blue bars, which are representing the host ranks. And then the blue bars representing the DPU that are working on behalf of the host ranks. Okay. So when the collective starts on the host side, like for example, on rank 0, the first thing that it needs to do is send a host arrive message from the host rank to the DPU, which represents itself. Okay, this host arrive message contains all the metadata that the particular collective includes. Like for example, in an all-gather V, then this host arrive message contains everything that the original all-gather V contains. Like for example, the source buffer address, the number of bytes that it needs to send to all the other remote ranks, and then the receive buffer, and then the displacement of the receive buffer, and then all the counts or bytes that it needs to receive into a receive buffer for each of these segments. But not only that, with this with DPU offload, as Rich mentioned earlier, we're using a very important technology here, which is called cross-government. So the benefit of cross-government is it allows you to do some of the memory transfers on the DPU side on behalf of the host. Okay. So to do that, first we have to register these host memories on host. And then we also send this data, including the memory keys that are pre-registered on host side, along with the host write messages to the DPU. So once the DPU receives this host write message, then it can start sending using the ring algorithm, and then start sending the ready to send message to other remote DPUs. Like for example, here it sends a RTS from rank 0 DPU to rank 1 DPU, including the cross-Gravami memory keys from the host rank. Okay, and then once the rank 1 DPU receives this RTS message, then it can issue a RDMA read operation from rank 1 DPU to rank 0 DPU. So the RDMA read happens between DPU and DPU. However, the actual memory transfers is happening as the dark dotted line here. The memory transfer happens actually between rank 0 on host. And then the data is read from the rank 0 host and then being written direct into rank 1 on the host. Okay. So even though the RDMA read happens between two DPU ranks, but actual memory transfers happens from host rank to host rank. Okay. So this is the beauty of it, and then how we are taking advantage of the DPU with cross-Gravami. Once the RDMA read is completed, then the rank 1 DPU will send an ACK to rank 0 DPU and then tells it, notifies it, okay, this particular operation has been completed. Then rank 0's DPU will keep checking on all these completions. Once it figures, okay, all the data that I need to send has already been sent, then and then all the data that I need to receive has already been received, and then it will send a DPU down message from the rank 0 DPU to rank 0 on host. This will mark the collective as completed on host. Okay, so next slide, please. So here I'm showing you some of the data that we collected from an offloaded AutoV. This slide shows you some of the latency data. This data was collected for a particular message size at 128 kilobytes. And you can see pretty much the DPU upload. By the way, the left-hand side is in a 1 ppm case, and then the right-hand side is a 4 ppm case. In this case, it's 32 ppm. So in both cases, you can see the DPU offload version of this collective can outperform the host versions quite a bit. If you have more PBMs or more nodes, basically meaning when your communicator is big enough, then this improvement is pretty significant. And next slide, please. So this is a non-blocking version of the latency showing for the same message size at 100 kilobytes. And this is even better when we're talking about within the non-blocking semantic. So performance improvement is pretty dramatic here. And next slide, please. So this one shows a very important and also interesting features of doing the DPU offload. So this shows you the non-blocking AutoV with the same 1 to 28 kilobyte message. But what it shows here is the overlap between the communication and computation. So here you can see for a 1 ppm case, pretty much as soon as you increase the node count to 8, then the overlap percentage between communication and compute can reach about 90%. Of course, the more nodes that we have, and the better. However, for the 4 ppm case, we almost reach 100% overlap, starting from like with only 2 nodes, with 4 ppm, 32 ppm in this case. So next slide, please. So based on this information, that we can conclude that basically there are a few of the advantages that we can gain from doing the DPU doing the DPU uploading of the collectives. One thing is that we can better utilize the network bandwidth because the lower latency in the previous slide that you saw basically translates to a higher network bandwidth that we are taking advantage of. And then the higher overlap percentage that you see in the last slide basically tells us that we can free up all the CPU cycles on the host side. And then we can use those CPU cycles to do some of the more important compute work instead of using them for the to progress in the collective itself. However, there's also some of these disadvantages with doing the DP offload of the collectives, which is for some of the latency sensitive message sizes, such as very small message sizes, because in that case, we are talking about a latency bound communication. In that case, because of all the overheads that we have introduced that are related to uploading to the DPU, like for example, you saw that we have to send host write message to the DPU, and then we have send the DPU back, and then we'll also have to send multiple of the ACK messages around. Those are all the overheads associated with this DPU offloading. And for those cases, then small messages are not going to be able to take advantage of that. So this is considered as one of the disadvantages. But currently, we are doing some research on how to take care of those advantages, and so we can make sure that we can also uploading small messages with to the DPU and still gain better performance as well. So this is still in progressing. I think that's all I have for slides. And so next, I think Jeff is going to walk you through some of the demos. Yeah, please, Jeff.
Okay, great. Thank you, Jan. Does anybody have any questions?
Can I ask a quick one?
Okay.
So it looked like all the performance improvement was quite good at 128K, but you mentioned small message sizes might not be so much.
Yes.
But have you measured, higher in the megabyte region?
Yes. For example, at very large message sizes, even a very naive implementation will be pretty much like a take advantage of all the full bandwidth. Like a 1 megabyte, right. That's something that we noticed, and there's very little difference between the two. Yeah.
Nice. And
because we already reaching full bandwidth in those cases, so even if you are just offloading that to the DPU, it's not going to get things faster. Right?
That makes sense. And on the system you're looking at, do you happen to know roughly where the cutoff point is, where it's
the cutoff for the small message?
Yeah, so yeah, maybe below.
So that's 32 kilobytes for most of our systems on Bluefield 2. And 16 kilobytes on Bluefield 3.
Excellent. Thank you very much. And I assume as well across collectives, that can vary as well.
Yeah, technically, yes. Yeah.
Yes. Yeah, very interesting. Thank you.
Interesting.
Okay, thank you. Other questions from folks? Okay, if you do have questions, feel free to put them in the chat. And thank you, Jan. So we'll try to jump to, so we do have kind of a UCC demo, and I noted that we were kind of testing some demos, and some of those I think didn't work quite as expected, possibly because the software stack is changing pretty quickly. So we do have kind of, as Jan noted, all the code here is open source for some of these things. It is a little bit complex, so we're kind of working on some scripts to make that easier to use. We will be, making those available, and we'll be on the Hot Interconnect Slack after the tutorial. We also will take some time at the end of the tutorial to kind of talk with you through some of these demos. And if you have any questions, we're happy to kind of run through them. Okay, so we have kind of a basic UCC demo here that Brad Suttlemeyer at NVIDIA did, and I'm going to see if I can run it. It is a video, and I think I just pulled it up. to make this easier. So let me switch to that. Okay. And so one thing that we know here, so we'll see a lot of stuff that is getting loaded. This is just an example of Brad is running kind of the all gather V with the OSU benchmarks. There's a lot of stuff here. He's specifying sort of his modules, a bunch of nodes, and what you see here is kind of some of the service daemons starting on each of those nodes. So on the DPU, have that Mimosa related service engine. It is take a while to do. So kind of see it spin up all the different daemons, and then it should do a little bit of computation and return a number back. Okay, and we'll look at this segment of code here in a slide in just a second. So don't worry if you don't get everything in it. It's perfectly okay. So here we see kind of the MPI all gather V and the test for different sizes with OSU MPI. Okay, and so that's it. So that's kind of an example there. So let's go back to the slides here and take a look at what actually happened there a little bit. Key thing to note is that this was run on the HPC advisory council nodes. So there are a bunch of different clusters there. There's one called Helios that has Bluefield 2 SmartNICs. They use the UCC all gather V algorithm that we just talked about. And kind of the steps as we saw, getting a node, running a JavaScript, launching 4 service processes on all of the GPUs, and then running the all gather V. Okay, so there's kind of an embedded video in the slides here. I think we'll see if we can share that or share the link for that video here in the chat. Just to remind everybody, talking about UCC, it is, sort of this complicated stack. It has a lot of different pieces to it. It does sit kind of on top of all these layers, things like verbs, UCX, nickel, sharpen, and just like shmim, kind of lower layers. Sort of what we saw within this demo here is that we saw things like, setting up certain transaction layers. We saw it using specific algorithmic primitives, so using all gather V, and then running some very simple benchmark codes. So we'll look at that crazy segment of code here. You saw that kind of scroll by, but one thing to note is that obviously this is a pretty long command. One thing I noticed that some of the stuff is open source, but is not fully productized. You might expect that if this was, ready to be released, say in a future version of the NVIDIA HPC networking stack or some other product that is related to that, some of this might be abstracted away from users. But key thing to note here, there are 2 parameters, your standard --MCA, enable collectives with the call _UCC_enable, specify a priority. You'll notice there's also hcall that's being enabled in the line before that. And then we're specifying a particular algorithm, within the UCC stack. So this red box here, we're saying UCC transport layer for UCP. We're using the all gather primitive to accelerate this offload. Then finally, we noticed that a bunch of these service daemons started, and so to set those up, there's this configuration file that is specified as part of the runtime. So this kind of details, how those service processes start up, and how they set up kind of that client server that we saw in the earlier Mimosa slides. Then again, just to go back and look at the very long, kind of screenshot here. This is from running the demo, and we see here that the daemon is starting. This is some of the output that you might see from that. Obviously, we don't expect you to get like a great amount of detail out of it, but just notice that it has some of these things like GPU offload service, and it's specifying the number of service processes per GPU. So each GPU, say with the BlueField 2, might have 8 cores, and here we're specifying that there are 4 of these service daemons. Okay, so any questions about the demo? I know we kind of run through that. Let me see if I can share in the chat here. I'll see if I can share the link. Everybody, if you want to go and watch that again, just to kind of see what's going on. I think this is an unlisted YouTube video, so it should show up for everybody. Okay. If there are no questions, we will move on to the next section, which will be talking about a different application space. So one thing to think about is, we kind of mentioned this earlier, that there are different ways that you can optimize for HPC applications for SmartNICs or for GPUs. Obviously, you can get better SmartNICs. So on the left-hand side here, we have something like these different variants of the BlueField, from the BlueField 2 up to the BlueField 4, which has tons of transistors. We have kind of improved frameworks. Here, we've shown Doka, but we just talked about UCC and how you might use that to accelerate HPC. And then we have revised algorithms, which we'll talk about a little bit more. Okay, so we'll kind of briefly talk about P3D FFT++, I guess. And one thing to note is that this is a C++ version of the Fortran-based P3D FFT package, which is used to implement fast Fourier transforms in 3D, and it also ties in with other FFT acceleration libraries like the 1D FFTW library. I will note too that I am presenting the section, but we do have I think Dimitri is on the call here, so he is the expert here, and I'm just sharing some brief information about it. But definitely, if you have questions about P3D FFT or P3D FFT++, he would be the expert to explain more details about the code itself. One thing to note is that P3D FFT++ is kind of an evolution of the original code. So a lot of effort went into the earlier Fortran code, and the newer code is C++ based with kind of an interface to the older Fortran version of the code. Okay, so one thing when we think about using a SmartNIC or a DPU for acceleration, especially with something like this distributed FFT solver, we think about how do we sort of decompose our compute and also our communication. And on the next slide, we'll kind of show an example of this. But basically with P3D FFT++, there are 5 different stages. There are 3 compute stages, FFT, memory operations, and transpose. And then there are 2 communication stages, both of the kind of all-to-all type variants. So obviously, when we think about the UCC primitives that we just talked about, this is potentially a case where you can use some of those to accelerate an application. As with a lot of HPC critical algorithms, communication is kind of the key bottleneck here. And so we'll kind of talk about how we can basically convert this algorithm from being something that is sort of a sort of blocking, more sequential type algorithm to something that is non-blocking, where we can overlap some of the computation and communication. As noted down here, basically we can pipeline, part of our batch algorithm, and then we can overlap some of the communication with that. So there's a branch in the repository. We do need to add that to the slide, but I'll share that in the chat, and we'll kind of show you the code here in just a second. Okay. So just to show you sort of what do we mean when we say, we're converting something from a blocking to a non-blocking implementation. And we'll see another kind of different variant of this in the next application. But here, what we can do is we can take some of the computation and communication phases, and we can overlap them, if they have variables that are independent of each other. Obviously, if you're updating a buffer that is used in a compute phase, you can't overlap that with other computation. The other thing that you can do is you can potentially increase the size of your buffers and get better bandwidth, as we noted that, for some of the very small messages, very, very small messages with some of the primitives, we see, worse performance for that, versus larger primitives. So here, we mentioned kind of the different stages, and we note kind of the top half here is the non-blocking version, and the bottom half is the blocking version. And so in the second case, we sort of overlap this. I think Dimitri noted that the performance on a BlueField 2 is about 25% better for most of the tests that they've seen. BlueField 3 is not quite as good, and it's not totally clear exactly what it is yet. BlueField 3 is a pretty new product. So there's probably more testing optimization to be done to kind of figure out, what is the best sort of computation overlap there. Okay. Any questions about P3D FFT? Okay. So normally this would be where we would do the demo. Unfortunately, the scripts for the demo didn't quite work out. So what I'm going to do is I will share the code with you, and we'll briefly look at it, and then we'll kind of come back to it sort of at the end of the tutorial here. So I'm going to share the code base in the chat here. Okay. Okay. Okay, so let's show to everybody, this is kind of the code base for P3D FFT ++. So this is the C++ version of the code. And the sample that we're kind of working on, which we'll sort of follow up with, is one of the C++ samples here. So this guy right here, the bench C2C. And a lot of these examples, you kind of specify a certain grid that you want to do your 3D FFT algorithm on. This one kind of picks some parameters for you, and so it's just kind of like a hello world of the P3D FFT benchmarking world. But one thing to note, if you want to pick this up and test it out, and we'll share a few scripts to help do this, you'd like to look at the non-blocking MD version of the code. There is also a version that uses persistent buffers, which gets a little bit better performance. But we note that this one is kind of, when we think about using sort of UCC collectives and offload, this is the branch that we're thinking about, the NV-NV branch. Okay, any questions, comments? Hopefully I did reasonable justice to this topic. And Dimitri, you can correct me if I missed anything. Okay. All right. So the next part of the tutorial is the DPU algorithms and the mini MD case study. I'm just checking to see where we are in terms of our schedule here, in case it makes sense to do a break. So I think what we might do here is we might do, let's say we'll do a break until probably 6:15. So we'll do kind of a short break, and then we'll come back. To say that we've got basically one more application that we're going to go through, and then we kind of have some future work, and we'll kind of have like a question and answer and hands-on and hackathon after that. So I'm going to go ahead and skip us to the break, and we'll break until my time, 6:15, 3:15 normal time, and we'll come back.
All right, see you then.
Yep, this you can tell this is the first time we run this tutorial, since we're figuring out the timing, but
Right.
But I think it's good to have breaks. So we definitely,
Yeah, much appreciated. Thank you.
Everybody stand up and come back. Okay, get started here again. All right, so we've talked about sort of two strategies for optimizing applications and HPC algorithms for SmartNICs and DPUs. So here we'll talk about kind of the what we consider the algorithmic approach. So here, we're talking about this application MiniMD, which is kind of a proxy application for lamps, and this is some work that a student of mine and Rich Vuduc at Georgia Tech did for a paper in IPDPS 2022. Okay, so just to start from the very beginning, MiniMD is a proxy app for a larger molecular dynamics simulation. The key thing that it does is it calculates the position and velocity of all these different particles at different time steps within the simulation. And so this is used, basically to, explore different phenomena of systems, including things like, maybe a kind of body, like a solution that has a bunch of different molecules within it that are interacting with each other, like typically happens within our bodies, for example. But in the distributed setting, you have to kind of take all these particles and divide them amongst MPI processes. And each process has its own kind of, data structures and buffers for its own particles, and it can kind of compute all the values for those. But then it has to also update the position of not only the pieces that it has, but it has to communicate that to other, processors. So one of the key things to note that for MiniMD and for a lot of these simulations, they have this concept of something called a cutoff distance. That is, a particle will exert kind of a force on particles that are closer to it, but farther away, the forces that it exerts may not matter that much in terms of the overall simulation. So this parameter, the cutoff parameter, specifies, how does that force interaction work, and also it makes the computation of, kind of the interaction between these particles easier to manage. One of the key things for MiniMD is that it has not only a cutoff parameter, but a neighbor list that gets updated between every iteration. So updating, these parameters within the neighbor list is very expensive. So the neighbor list is basically like a buffer that allows you to kind of compute things locally and then also communicate those with your neighbor. Between processes, MPI processes, there's a concept of a ghost zone. That is, you have to communicate your state to your neighbors. The cutoff distance specifies the interaction region for a particular set of processes, but if that intrudes into the ghost zone, then that data has to be transferred to the other nodes so that they also can update, their particle movement and velocities. So particles might also move across processes at some point. This causes another communication update and overhead. And so then you have things like, updating your neighbor list, doing these boundary region exchange, and then also moving particles from one MPI process to another. So this doesn't necessarily happen every iteration with MiniMD, but it happens, say, every, in iterations. Okay, so now that we have kind of a high-level view of what MiniMD looks like, we can look at sort of the algorithmic structure. On the left-hand side, of course, we have our image with 4 processes. On the right-hand side, we have kind of the algorithmic view, where it is updating this velocity of the particles, updating the position, and then it is basically saying, okay, do I need to go through and do that process of updating my neighbor build, or do I just exchange data about things that are within the ghost region between MPI processes? So depending on whether you're at one of those intervals where you need to do the neighbor build, in one case you might just do communication, and the other case you might exchange data, and then all of these sort of neighbor lists will get updated in that second category. Then again, you sort of go back and you compute the force on the particle and its velocity, and then you go back to the beginning and do that in each iteration. So one of the key things is that each of these you might be able to parallelize, but the entire process itself is sequential in some sense. So when you think about restructuring the algorithm, there are certain parts that you can parallelize and certain parts that are pretty sequential and static. Okay, so when you think about the serial dependencies, we'll look at sort of the application, and then we'll point out each of the pieces of that. Here at the bottom, we have the number of iterations, so starting from I going to I plus 4. And then we look at things like, what is the actual computation? Here we have the force computation. And then we have the velocity update, UV. Then we have that kind of intermediate step, we're rebuilding the neighbor list, doing our kind of data reorganization, and potentially, sorting values. And, that has a dependency on upcoming computation elements. So, the neighbor build itself introduces a dependency into this process. Then we have things like communication across API processes, and also additional, data reorganization and communication across processes, that comes about because of particles moving between different, parts of the simulation and across API processes. Okay. So, one of the things we originally thought when we thought about optimizing this for the blue field is that we thought it might make a lot of sense to take something like the neighbor list rebuild, which is sort of a sorting based algorithm, and move that to the blue field. I think what we found is that, the neighbor build was actually slower on the blue field too, because the blue field 2, didn't really have, it had sort of a slower processor. It also didn't have a lot of optimizations in terms of like easy to use vector instructions. Obviously, the ARM cores on the blue field 2, you can use Neon, but there wasn't anything like SV, or on the host, had some sort of AVX based intrinsics that could be used to optimize things like sorting. So when we think about breaking dependencies, one thing that we can do is we can take that actual computation and potentially move that to the blue field. And so in what we call the off-path algorithm, that's exactly what we did. We took the force computation and did that in parallel with some of the other processes. And obviously the neighbor build creates a dependency on upcoming iterations, but for the current iteration, it doesn't necessarily introduce dependency there. So these two pieces of work can execute in parallel. But you'll notice that we left the neighbor build on the host because the host is better at performing that type of operation. The other pieces that we can move are a little bit of the communication. So some of the things that you might expect. So when we think about communication with collectives or offloads, or related efforts like with Mbappage, where you're doing sort of collective offload. This is the same situation here, where we put a little bit of that communication explicitly on the blue field, and these are things that don't have dependencies, on the rest of the algorithm. So to test this, like a lot of the stuff that we've done here, we used another cluster in the HPC Advisory Council testbed, one called Thor. At the time we ran this on the blue field 2 with a ConnectX 6 HDR networking adapter, and a Bluefield 2, which had 8 ARM D8 A72 CPUs. Obviously, they run at a pretty reasonable frequency, so 2.5 gigahertz for that, for the cores on the Bluefield, but they're not quite as beefy as the Intel Broadwell cores on the host. So one thing that we can note here is that, let me click through. Okay, so if we're thinking about in terms of, somebody have a question? Okay. So one thing that we found was that when we sort of overlap some of this computation and communication, is that we noticed some small but noticeable speedups. So we got speedups of about 20% compared to the host-only execution. One thing we noted in the paper is that if you think about having a network card, say something like a ConnectX or some kind of InfiniBand adapter, if you were to replace that with the Bluefield 2 in this case, then the overall power add was pretty minimal. I think we said it was something like 6%. I think that was assuming maybe that she had even lower power NIC than something like a ConnectX 6 or 7. But basically we said in terms of the power increase, the performance increase was pretty noticeable. So one big question that people have is, if I'm going to rewrite my algorithm to map it to something like a SmartNIC, shouldn't I just buy a bigger host? I think the argument here is that your system needs networking, it needs high-speed networking. Communication is a big bottleneck for a lot of HPC applications. And if you have this added capability where you can overlap some of the computation and communication, then even better, you can get even better performance. The other thing that we noted in this paper is that, one of the key things, if you restructure an algorithm, you have to check and see, does it actually still work? So does this actually, predict the values that I need to predict as a scientific simulation? And we noted in this case that, the baseline and what we called the off-path approach using the Bluefield, were very similar. Okay. We also ran MPI and OpenMP results, so kind of performance sweeps with this code. One thing that you note is that if you just run stuff on a bunch of host cores, you'll probably do better, at least for this particular case. But there is kind of a knee in the curve where if you say I match up a certain number of OpenMP threads on the Bluefield and MPI, ranks on the Bluefield on the host, then I can get better performance overall. One key thing to note here is that we really didn't optimize for any of the vector extensions on the Bluefield. Probably if you're running something at scale, that would be something that you would do. And especially with like a Bluefield 3 or with like a newer NIC that has something that's like a CPU, you'd want to make sure that you're getting the most possible performance out of that compute that you could. So here we just note kind of the knee in the curve. So you see how the Bluefield, which is the orange, purple, pink, and light green lines, and how they compare with the kind of teal line, which is sort of the host-only approach. One, kind of limitation that we noted, and one of the reasons that some of the software stacks that we've been talking about are so important, so things like Mimosa, which are weren't available when we were doing this paper and are not fully released as a product yet, is that there is a lot of overhead in terms of things like thread synchronization. Probably in this case, a lot of it was OpenMP synchronization from kind of shared variables and data structures that were locking against each other. But say for going from 1 core to 8 cores on a Bluefield, we got about 2.5 x speed up, which is a little bit worse than what you might expect. but it's still pretty good. So one of the key things to note here is that when we think about algorithmic restructuring, obviously this is a pretty extreme approach. And so this is if you have an HPC application where you say, I might want to, maximize the performance of this application. I think Dimitri did some of that with P3D FFT and converting from blocking to non-blocking. That is sort of a type of algorithmic restructuring. Here in this case with MiniMD, we've done sort of a more extreme example where we tried to move as much of the computation and communication to the blue field and sort of overlap things wherever possible. Right now, we're looking at trying to do this for AMG type applications. So I think in the beginning, David mentioned that we're looking at stuff like Mulu. And there we're also kind of looking at the same kind of things where you take a framework in this case and you try to overlap the computation and communication. But I think the key thing to note here is that this is a wide open area for research. So this is not something that is solved. And as you can see, from this effort here, it's pretty challenging to actually do this. So you do get good performance, but it also takes a lot of work to actually do this restructure. Okay, so we're going to jump over the break since we broke. And we'll do a little bit of a demo. I think this one, one thing here, we'll probably come back to this at the end. But one thing that I want to note is that this is kind of weird when you look at the other example that we had. This actually, in this case, we took MiniMD, we compiled two different versions of it. So we have an x86 version of it and a ARM based version of it. Here in this example, we're running one of those tests that you saw on the previous slide with the results. We have a certain number of processors, and then we have a certain number of threads on the host, on the blue fields. So we're kind of doing some of those design curve studies. The commands look very similar. You're passing in some number of hosts, and then you're passing in a different executable with a different number of threads. This is kind of interesting. I had never seen this until the student started done this. You can actually launch an MPI command and give it multiple applications to run on different architectures. So this right here is doing an MPI run of the x86 code and also launching the ARM version of it. You'll notice here I'm running on Thor Bluefield 3, one of the nodes there. We can go through and run some of the host and Bluefield versions of this if anybody's interested. One thing I'll do is that I ran this morning and it worked on Bluefield 2 and Bluefield 3. Unfortunately, there's some kind of runtime here that we need to work through. So this one at the moment doesn't fully run, but we do have the scripts for this, and I think we have the code available. Yes. So I'll paste this into the chat for folks. So this code is a little bit is pretty close to being ready to run. We do need to test again on Bluefield 3. At the very end here, we're going to talk about different test beds where if you're interested in doing work with SmartNICs, you can kind of pick this code up and work with it there. I think the weird thing here, just to go back real quickly, this doesn't work if you launch it from the host and run it to the Bluefield. But then again, we're not using any of the stuff like the service daemons, the Mimosa and UCC collectives. You could imagine that if we had incorporated some of that, running this application would probably be a lot easier than how we're doing it here. Okay, so I'll share this in the chat real quick. Folks want to go and kind of look at it. Does anybody have any questions while I'm doing that?
So it sounds like algorithmic restructuring can be challenging. And I'm wondering if you have any suggestions on best practices for identifying, say, which components should be offloaded and which shouldn't.
Yeah, that's a great question. I think probably obviously it all starts with profiling, so you have to kind of determine what are your computation communication phases, and what you're trying to do is sort of also think about it in Amdahl's law way, where okay, presumably I have some code that has some parallelism via MPI. Do I have additional parallelism within like the compute region? If so, how long does it take? So like, in this case, if we run it multi-threaded and we find, okay, if I just run it multi-threaded and it's really fast, the force compute is really fast anyways, maybe it doesn't necessarily make that much sense to move it to the blue field, which has fewer, slower cores. In this case, I think the force compute took a long enough amount of time that you did actually see a benefit from moving it, from the host to the blue field. But of course, then if you put it on I don't know, let's say one of the latest AMD systems with, like 64 to 128 threads per server, you might get a different result. You might say, okay, actually, that doesn't make sense to offload, and I should just offload the communication. I don't think we fully codified the best practices. This example, we kind of started out, like I said, we try to do the neighbor build first because we thought very naturally, oh, okay, this is something that would make sense to do, but it actually turned out that the blue field was not very good at accelerating that. As in, it was so slow that it became the bottleneck of the application. We're kind of doing like a variation of that with AMG, where you have sort of the coarse and fine grain meshes that you compute, and you can sort of do those in parallel. And I think the idea there is that maybe a coarse grid or mesh, you can do that on the blue field at the same time that you're doing like a slightly more fine grain or some other portion of the algorithm on the host. But yeah, the short answer to your question is probably lots of profiling, figure out the compute and communication phases, and then just try to test, sort of mapping some of those across the devices. A lot of these things would be a lot easier if it was easier. Right now, it's a little bit difficult to exchange data between the host and like especially a blue field device. For our case, that was one of the big limiters, but some of the things we're talking about today would actually make that a lot easier. And then if you think about something like OpenMP offload, that might make it really easy to say, okay, I have an OpenMP kernel. I'm going to test it on the host, and then I'm going to test it on the GPU. So, all these things that are kind of people are building that are not quite ready, but hopefully will be soon, would make this process a lot easier. Yeah, thanks.
Yeah, thank you. That's great info.
Yeah, overly answer your question.
And
we do have pieces
more silly questions. I get some more questions from others.
Yeah. Does anybody else have any questions?
Yeah. Maybe one more quick thought on that. I wonder if it seems to me like this might be a great application for performance modeling of say a SmartNIC enabled system. Maybe it could help with this challenge.
Yes.
Yeah.
So the paper we did.
Done. Oh
well, I mean, not fully. I mean, I would say there's a lot to be done. The paper that we did a performance model for mini MD. So I think we at the time Bluefield 3 was not out, so we kind of speculated on what we thought the parameters for that might be, and then I think sort of did like a mini study that said, okay, if you tweak this knob, this is how your performance would change. The problem is that I think that was interesting. The problem is it's not, the reason I didn't include it here is because it's not really generalizable. Like it works really well for this application. So I think that's an open area of research. I would say is how do you make it easier to do application specific performance models for these types of systems, or how do you make a more generalizable model? But yeah, we don't have the answer yet. So.
Interesting. Thank you.
Okay, thank you. Okay. And kind of at the end here, I think I have a Thor session still up. We can look at this piece of code, and I can show you what runs and what breaks, and we should be able to fix it shortly. Okay. All right. So we're kind of in the home stretch here. I think we're scheduled for 4 hours for this tutorial. We'll have kind of a longer portion at the end for question and answer and kind of hands-on. So we'll kind of dig into some of these demos in a little bit more detail as people are interested. Obviously, we know that it's Friday, and if folks have learned enough, that's okay too. So thinking about kind of future directions, obviously. Performance modeling, we should probably put on this list. I think it's definitely one of these, but lots of different things that we're thinking about, different types of applications, which especially HPC applications make sense. If you go back to Rich's kind of introduction, you'll notice that a lot of these DPUs are meant for things like running management servers, for security and privacy, for providing like isolation, between maybe the SmartNIC and the host. But people really haven't thought about them in context of HPC as like an HPC accelerator. So, there's a couple of papers here that look at stuff like compression, which is kind of a key component of a lot of these HPC workflows. That would be pretty important. Oscar mentioned task-based runtime research. I think I noticed in one of the slides too, it said something about Parsec and Legion, which are kind of traditional HPC focused runtimes. So kind of mapping those to DPUs. Things like edge computing. One crazy idea that I've heard is, what if you had like a more computational powerful like SmartNIC, and maybe you put that in either like a smaller system or like an older system. So in that case, you have kind of a like an edge computing device. So it might be right next to where your data ingress is. And then I think a lot of the AI and machine learning applications are still kind of in progress. So we have some initial ideas, which will probably evolve over time. But none of these are like fully solved or fully fleshed out. These are all pretty active areas of research. I just want to mention here, we didn't spend a lot of time talking about it here. Happy to go into detail and answer questions. Obviously, I'm probably not an expert on Doka, but I do want to point out that this is one of these frameworks that has a lot of pieces to it. So this if we look here at kind of the purple box, it has stuff like crypto support for the data plane development kit, obviously security, storage. We talked a lot today about UCC and UCX, but then there are a lot of other things that we haven't really touched on that much here. One other kind of framework that we haven't gone into a lot of detail on, but you probably could do a full tutorial about, is P4. So this is kind of a vendor neutral specification. It is a little bit lower level, I guess I would say, than some of the things we're talking about. So today we talked about a lot of things that interact with MPI and OpenSHMEM and potentially OpenMP. P4 is sort of the packet processing level, so it's not really the application level like what we've been looking at here, but it is a very important standard. And over here on the right, kind of a figure that we pulled from p4.org that shows where you might have like an application, you're doing something like packet classification, you're potentially doing like routing, forwarding, or filtering, or some other operation, and then there's a compiler that maps sort of in a vendor neutral and potentially a target specific way to a certain piece of hardware. So we mentioned on the slide for the AMD SmartNICs that there was the FPGA based Alveo NIC, which has this shell they call OpenNIC, and then a group associated with Berkeley and NERSC, ESNet. They took that framework and they implemented P4 inside of that. So then you have kind of an FPGA based SmartNIC that is implementing this industry standard, packet processing, API framework. So that's just kind of interesting and cool. It's relatively complicated to use some of these things, but we put some links. Doka has kind of a nice free kind of training video that you can watch, and P4 actually has this pretty interesting web interface where you can go to that site and you can actually write some like P4 programs and see what it looks like to actually do stuff with that. All right, so we're kind of getting close to the end here, but one of the key things we want to notice that you can access SmartNICs via an increasing number of test beds, and I should call out all the folks that are doing this tutorial have benefited from HPC AI Advisory Council cluster, that has high speed NVIDIA, formerly Mellanox switches, things like Bluefield 2 and 3. So these have been used for other hackathons, CPU hackathons. The International Supercomputing Student Cluster Competition had a component this year where they had to use the DPU to accelerate some small piece of an application. I myself are in the second thing, the Crunch Rose Gallery testbed. We have a couple different SmartNICs. We have a lot of FPGAs because people like those for novel architecture, and a few other things that we purchased recently, which are kind of fall in the IPU Intel FPGA based SmartNIC. So this last one here, I think, is like a P4 compatible SmartNIC that you can just kind of test out. So too that Oscar, works with Oak Ridge National Lab. They have a open access testbed. We have to apply for it, called Wombat. They have Bluefield 2 and 3, along with a lot of interesting ARM hardware. There are folks at Los Alamos that also have testbeds. If you're interested in that one, we can put you in touch with the PI, but I don't think they have a webpage. And then I would be remiss if I didn't notice that AMD Xilinx has this program they call Exact or Hack, and so you can potentially use like an AMD Alveo for some kind of open NIC type framework stuff. So we put all the links here. Definitely we encourage you to check those out. You can apply for counts. Probably I would pick one because every environment is different. One thing I've noticed from my test bed and from Wombat and from the HPC Advisory Council cluster is that all of us have slightly different software stacks. So it's best to get something running on one test bed and then try to port it rather than try to tackle multiple test beds at once. But a lot of these you can apply to and have sort of varying access requirements. So for instance, the one I run is NSF funded, so pretty much anybody in the US can get pretty easy access to. Okay. Yeah, thank you. And Matt noted in the chat here, so you can put a SmartNIC in an older system and kind of use that as sort of a bridge between a sort of an older operating system. You know, he mentioned Windows XP, but I hope nobody's running that on their critical infrastructure. And then, you know, typically like Linux, like Ubuntu or Red Hat on the SmartNIC itself. I will notice that, you know, not all the DPUs that we mentioned run OSs. So the ones that just support P4 or FPGA stuff. But when we think about things that run operating systems, the Marvell Octeon, the NVIDIA Bluefield, and potentially like an FPGA, but that is pretty complicated, and we won't go into that here. Okay. Great. So now I think we have one or two more questions for you. And I'll also take this time if other folks have questions they want to ask us. Let's switch over to our multimeter here. Then we'll kind of have a general sort of hacking type. Okay. So we have kind of a general questions thing. If you have any questions, feel free to put them here, or you know, yell them out, or raise your hand, or anything. And then we've got one more question. Okay. For a minute or two here. Okay. So we're going to ask you one more question here. And the big question is, how can we improve this tutorial? We know that the demos and stuff and kind of hands-on are pieces that we're kind of working to improve, but you know, we'd be interested to hear if you have other suggestions on topics that we didn't talk about. You know, if there was something that you wanted to hear about that we didn't cover today, you know, that'd be really good feedback from everybody who's. While we have this ask, are there application-specific tuning parameters that change to get good performance on the DPU? Yes. So I can't speak for all applications. I'm most familiar with the ones that we've worked on, which are kind of the extensive algorithmic restructuring. But you know, in our case, I think one thing that we found is that you can change a bunch of the different parameters in terms of how often you sort of you know, do this re-neighboring process. So basically, where you rebuild the entire neighbor list, and that is something that we didn't move to the DPU. But we did find, you know, if we kind of tweak that, then you know, the trade-off is if you tweak it too much, then your application output, you know, no longer matches your baseline. So you're potentially not getting quite the right answer. But we found that if we kind of tweak that, then we got better speed up from sort of the overlap. And I forget exactly what the values were. So
there is also maybe Jon can elaborate a little bit more on this, on what tuning parameters can be done in the context of Mimosa. And when you use the DPU as an offloading device, for, in this case, would be MPI collectives. I know for sure that you can play with the number of service threads that you have in the DPU. And that may give different sort of performance. that you may have, and I'm sure they have done. His team has done a lot of experiments in this space, but there may be other parameters that could be tuned.
Yeah, Oscar is definitely correct here. So basically, I think this question is too generic to answer in detail without knowing the context of what specific kind of offload is asking for. Like, for example, in the case that Jeff is talking about the mini MD, which is most likely leveraging, like, offloading the compute part to the DPU. And the characteristic of that kind of offloading is definitely different than offloading collective to the DPU, which is in our case. So in our case, Oscar mentioned that we can tune something such as the number of service processes that we want to run on the DPU, which was also shown in the demo earlier. And in addition to that, we can also tune things like how many concurrent stands and receives that we want to do in each of the progression cycle, and how many collectives that we want to progress in each cycle, and something like that. So that we can reach some kind of balance or trade-off between the compute part that we have to drive the collective progressing and the communication part as well. So this is much more like how are you going to better leverage the limited amount of a CPU resource on the DPU, and perhaps somewhat a much better network resource or memory bandwidth resource. So we have like all these three kinds of different characteristics from the performance perspective that we can try to balance among them. Yeah.
Yeah, and I think just to add to Jan's point, which is very good. We've thought a little bit about obviously the much better network of the DPU is kind of a key part of thinking about how to sort of optimize an application. One thing we have looked at is the DPU in many cases has a much better what's called flop to byte ratio. So it has like most of these big servers are very compute heavy, and the memory bandwidth is very limited. But if you have an application that is not like super compute heavy and potentially has like high communication costs and also needs a more balanced memory bandwidth. I think a Bluefield 3 has like 2 channels of DRAM, so it's not like server level, but you balance that with the fact that it really only has 8 kind of reasonably fast cores. Then you have kind of a better compute to memory bandwidth ratio. So that's another thing that could affect like is really based on the application, but that could affect how good performance you get. Okay. Other questions from folks? Okay. We've got some suggestions, things to talk about, and kind of add more slides about. I think definitely, security applications probably would fit pretty well. I think one thing that this tutorial is kind of unusual in that a lot of them talk extensively about security, and we basically don't talk about it. But definitely, I think that's something that we could probably include and talk about how that might make sense. One thing that I have heard, and maybe Oscar can speak more to, is with a lot of these like HPC clusters, I don't know if they've really thought about security other than potentially if you're running like container workloads. So you might want to have some kind of isolation layer if you're trying to run a container. So Oscar, not to put you on the spot, but if you have any thoughts about that.
Well, there is basically, I call it a killer app in the context of using the DPUs to accelerate the security aspect of applications now that our workloads in supercomputers are becoming more machine learning and with new types of applications, like for example, medical data and privacy and so on. Traditionally we have dealt with the issue of basically being secure from the outside, but not secure from the inside. So potentially the use of a DPU for having secure communication in the network, as well as so that data cannot be intercepted inside in a shared resource like a network. That's also definitely a big use case, as well as data at rest, basically accelerating that aspect of in storage. But on the other hand, we are also coming in the situation that the supercomputer basically acting as a coordinator for what we call a federated or distributed machine learning workloads, like in this case, going back to the medical example, where basically we have for example, hospitals dealing with patients' data, basically doing training, local trainings, and then connecting to a supercomputer, and we need to have fast, basically, operations there for securing that sort of communications, and also inside the supercomputer, accelerated through a DPU, potentially could be something along those lines of some data sets could be remote, some of the data sets could be inside the computing center. So handling that sort of situation is definitely a killer app for the DPUs as a way not only to accelerate the encryption processes, but also handling the keys distribution and securing all of these sort of things. And those are the things that we feel like make sense from our HPC perspective to focus on. Yeah, so far this tutorial has been focusing on our traditional modeling and simulation applications, but definitely DPUs are basically provide benefits in many areas and different basically say can have a multidimensional value from the point of view benefiting performance, or also security, sharing of the resources and things like that, multi-tenant type of management of compute of resources and so on.
Great, thank you, Oscar. Yeah, and let's see if we can go back to our. We had our. So these are kind of our categories. These are things that we think SmartNICs would be good at. Obviously, encryption. I think Yang noted that for blockchain, kind of Web3, and Oscar kind of reiterated for HPC. The security encryption would be kind of a key part of that. Obviously, communication offload and acceleration and compression. Kind of surprised to see compression is the most important for attendees, but it could just be the selective nature of attendees we have. Okay. All right. So let's see. So I think too, thank you for the comments. Definitely we had kind of a limited amount of information on DPUs with FPGAs. Some of that is because those tend to be harder to use, to be honest. I'm definitely a fan of those, and we have a lot of those in the test bed I run. But they are a little bit more difficult to kind of tackle. So happy to talk with folks about resources for that, for people who are interested. And obviously we have a few of those on our test bed that we have people kind of looking at, like OpenNIC related stuff. Okay, let's see. So another question.
Yeah.
Is RDMA well supported on DPUs? I don't know if someone else.
I was trying to answer this question in chat window, but
Oh, okay, that's fine.
answer here. Yeah. So basically, I think this question is very product specific, because this is different vendor may choose to implement that a complete different way. Like for example, in NVIDIA's Bluefield product series, basically we have a ConnectX component on the DPU, right? So RDMA is supported there naturally, and then Atomic is also fully supported.
Yeah, that
I'm not
that
familiar
makes
with
a lot of sense.
other vendors' products.
Right. That makes sense. Thank you.
Yeah, and I think to add to Young's point for like FPGAs, I think it kind of depends. I honestly forget what the Alveo ones, but I know like some of the different Intel FPGAs that people are using as SmartNICs. You know, they for the longest time they've had basically like a software kind of networking stack. So for those, I would say RDMA is not well supported.
Right.
But yeah, you are kind of benefiting with the Bluefield, and that is, I don't want to say it's tacked on, but it has both the like the traditional IB Ethernet, you know, hard network IP, and then also this additional functionality.
Yeah, it's an interesting design. ConnectX 6 is on Bluefield 2 and ConnectX 7 on 3.
Yeah, that's right.
Okay. Yeah. Yeah, it's powerful.
Okay. So let's see. So I think, you know, we're kind of at the end of our slide presentation. You know, I know I and Oscar can stick around for anybody that has additional questions. If you want to try to take a look, I can show you some of the mini AMD stuff on a terminal, but I think I would say we would kind of consider this the end of the tutorial as it currently stands. Definitely, if you have additional questions or comments, you know, please feel free to stick around and ask them. And thank you to all our speakers. I guess I would say thank you to kind of in order. I think we had Rich Graham, Oscar, and Jan, and thank you to Dimitri for the code example. And thank you for everybody who joined. Thanks, Matt.
Before we go, we also, you know, we're trying to build a community around SmartNICs to understand more and their use cases, and we are putting together. We're gonna have another version of this tutorial at Supercomputing in November in Denver, and we hope to have the OpenMP offload examples from Barcelona, a supercomputing center, so we can demo those pieces in the tutorial. And yeah, we want to build the community, and also we also have some birds of feather that got accepted, and we can continue a little bit more discussions. But I really feel like identifying those motivating use cases for the SmartNICs is key to make sure we are basically tackling problems that we can leverage them for, and that will definitely drive basically a lot of the development of the stack.
And I think we should note too that there's like a DPU workshop, I think, Oscar, that you helped organize at ISC this year, and I'm assuming there'll be, you know, kind of there's a bunch of DPU hackathons and things like that. So there's a lot of opportunities to kind of be involved. Okay. Well, any other questions for anybody? You're free to go if you don't have any questions, or if you'd like to hang out and ask us a question, or we can look at some of the code examples we had as well. Okay. Well, thank you, Yang. Thank you, Dimitri. Appreciate you guys hanging out.
Yeah, sure thing.
And David, I guess I think we uploaded a copy of your slides. We'll probably share one more with Rohit, and we'll kind of post some stuff in the Slack here as to the different resources we have.
Sounds great. Thank you very much.
Yeah, we didn't go the full 4 hours, but I think some of those the OpenMP stuff was not quite ready. So,
Sure.
I mean, I can talk for another 45 minutes, but no.
Yeah, I don't doubt that you could have done 4 hours, right?
That's I think we may actually have to condense some stuff for the. I think the next time we're going to try to do this, we have 3.5 hours, so we may have to consolidate some stuff. Okay, are we I think there's one more tutorial still. Are there 1 or 2 more tutorials still going?
Good question.
I think I saw one that
Oh
started.
yeah, LibFabric is going on right now, I believe.
Yeah.
So I might go catch the end of that one.
Okay.
Thanks very much, guys. That was a great tutorial. And,
Well, thank you for your help.
yeah, yeah. I was just about to say, it seems like you really don't need my help. You guys could host the thing yourselves. You're undoubtedly familiar with doing this.
Well, that's we've done a lot of these, but it's always very
Right.
nice to have.
Have a
I
little
mean, as you can tell, some things weird happen, like when Rich left, and
Oh, sure. Yeah.
yeah.
Oh, and
Well-
yeah, we lost at least 8 people, I think, there.
yeah,
But
yeah,
maybe that's okay. Maybe they
yeah.
were
Yeah.
barely attending anyway.
They were not SmartNICs super fan. Yeah. They were going to go to the other one that didn't pick them
Right.
out, I guess.
Yeah.